Hello everyone. In this video, I'm going to talk about how to set up molecular orbital diagrams, how to calculate bond orders for some simple diatomic molecules and ions. In our previous videos, I already talked about how to find these diagrams for s and p orbitals. I'm going to remind you for this video, I'm going to focus on homonuclear diatomic molecules and ions. First example we are going to review is hydrogen, H2. As you see here, this is the homonuclear, both atoms are identicals, and we are going to set up our molecular diagram for this molecule. Hydrogen is made of two hydrogen atoms, H and H. So we need to know electron configuration for each element that we are going to involve them in the molecular diagrams. H is going to have this electron configuration, 1s1. I'm going to write on the left side hydrogen, on the right side hydrogen. It means in the left side I'm going to focus on only hydrogen atom with this electron configuration 1s1, and on the right side another hydrogen atom 1s1 as well. We are going to add our electrons here, one electron here, one electron here. It means this is the electron of hydrogen that we have in 1s1. Then we are going to add our electrons from atomic orbitals to molecular orbitals. Based on the Hund's rule, we are going to do the same thing we did earlier. It means we are going to add electrons first to fill out the orbitals with one single electrons. Then for the second one, we are going to have opposite spin. Opposite spin. So let me draw that one more time. So whenever we are going to pair electrons in each orbital, we knew that we have to have two electrons and they are going to fill out by single electrons. When we have a pair of electrons, the second electron should have opposite spin. So at this point, we are going to have two electrons here. Let's label our molecular orbitals. So the first one is going to be called sigma, and the second one is going to be called sigma star. So let me write that one by better writing. I'm going to write is sigma, and the top one sigma star. Bonding is sigma, anti-bonding sigma star. Because they are made of one s, I'm going to write one s for each of them. Like electron configuration, we are going to write this information for H2. So we are going to say that sigma 1s, it has two electrons. It has two electrons. So please look at the diagram. I'm going to remind you in our diagram, we have two electrons in sigma 1s. Then I'm going to continue writing in sigma star 1s. We don't have any electrons. As you see here, there is no electrons here. So I don't need to add any electrons here, or you may write 0, because it doesn't make sense to have a molecular orbital with no electrons there. So we are going to cross that one. So you don't need to keep that one here. I'm going to erase it here. So it looks hydrogen has this molecular orbital diagram with this configuration. Always we do have one calculations based on that outcome. Bond order. Bond order is basically defined as half of number of bonding electrons minus number of anti-bonding electrons. Anti-bonding electrons. So bonding electrons minus anti-bonding electrons. So let's practice that one for this hydrogen. Bond order for our molecule. The number of electrons in bonding orbital is 2. So let me write that. This number is 2 minus, and there is no electrons in the anti-bonding here. There is no electrons in the anti-bonding here, 0. So when we are going to calculate that, it's ending to bond order 1 for hydrogen. So we are going to say that bond order of hydrogen is 1. And we could easily say that this is the for hydrogen is correct one. Keep in mind, if we are going to have bond order greater than 0, it means our species or molecule ion exists. So bond order greater than 1, it means we do have our molecules. So definitely 1, it means we can see like this one as well. Let's practice talking about another example like H2 minus. Let's see, do we have this ion hydrogen 2 minus? So if we are going to work on this, I'm asking you to consider that H2 minus, it means we have two hydrogen atoms, and one of the hydrogen atom, it has one negative charge. So it looks we have one atom added to one anion, and this combination made H2 minus. I'm going to ask you to remember that for hydrogen, we need to write 1s1. And whenever we have negative, we are going to consider that they absorb electrons. So it means we are going to change that one to by adding electron 1s2. Right now, I'm going to write on the left side hydrogen and on the right side hydrogen 1 negative. Electron configuration for each one, 1s1, and for the second one is 1s2. This is something we have based on what we said earlier. Number of electrons we have, we are going to add to each side. 1 electron for this, and because we have 2 electrons here, I'm going to add 2 electrons for atomic orbit. This is the time to add our electrons to the molecular orbitals, to add our electrons to molecular orbitals. So we do have 3 electrons totally, 1 in the left, 2 on the right. So I'm going to add 1, 2, please pay attention how I'm going to fill out the molecular orbitals. I'm going to label them. I'm sure everyone can easily label them. This is the sigma, this one is sigma star. And because they are made of 1s atomic orbital, so they are called sigma 1s and sigma star 1s. Let's write for H2 minus what we have. Sigma star, it has 1 electron, and sigma has 2 electrons. So I'm going to add 1 electrons and 2 electrons here. This is the what we get from the molecular orbital diagram. To calculate bond order, again, I'm going to remind you, half of number of bonding electrons minus number of anti-bonding electrons. Anti-bonding electrons. So to have a simple calculation for bond order for H2 minus, I'm going to say half of 2 means these 2 minus 1, excuse me, it should not be the correct one, maybe this one, minus 1. So I'm going to subtract that one. The answer is going to be like this. As I said earlier, when we have bond order greater than 0, if we have bond order greater than 0, it means that ion or molecule exists. Interestingly, experimental research, experimental outcomes confirm, verify that we do have H2 minus. So this is one of the advantages of this theory, molecular orbital theory. Also, you know that if we are going to have the number of electrons in bonding molecular orbitals, it means we are going to have more stability. More electrons in bonding, it means we are going to have more stable. Less electrons in anti-bonding means more stable. So I'm going to talk about stability here. More electrons, let me write in the by better handwriting, more electrons in bonding, less electrons in anti-bonding. It makes more stability, more stability. So let's compare this one with the previous example. In the previous example, we did have 2 electrons in bonding and no anti-bonding electrons. No anti-bonding electrons. In here, we do have 1 anti-bonding. So it looks H2 is more stable than H2 1 negative. Right now, I'm going to focus on another example like H2 plus, H2 plus, and see how it works for H2 plus. So let's move a little bit faster, talking about 2 hydrogen atoms, and one of the hydrogen, it has one positive charge, one positive charge. So I'm going to say that hydrogen 1 is 1, and other hydrogen is H plus is it doesn't have any electron. I'm going to write 1s1, 1s0, or you are going to say H and H plus. 1 electron should be reported here. And then you are going to have 1 electron here, no electrons for other ones. As you see here, we are going to have like bond order 1 minus 0, we are going to have like this. I may ask you to look at the bond order for hydrogen H2 1 negative and H2 1 positive. 1, 0.5 and 0.5. We are going to see which one is more stable. Definitely the correct answer is hydrogen. More stable in this series. More stable. And let's see which one is going to be next. In the previous example, I said when we are going to talk about stability, more electrons in bonding and less electrons in anti-bonding determine stability. Between H2 minus and H2 plus, so we have 2 electrons in bonding, and here right now we have 1 electron in bonding. So here we have 1 electron in bonding. Even we have anti-bonding electrons for H2 minus and no electrons in anti-bonding for H2 plus. But the most important factor determines stability is having number of electrons in bonding. So here 2 electrons here and 1 electron here. So we are going to say that next one to be stable is H2 minus and is going to be least stability in our series. Again, if you are going to set up the write that, you are going to write 1 sigma 1s for, excuse me, let me write H2 plus. You may write sigma 1s 1 electron. We are going to set it up for any other diatomic molecules with period 1, period 2, period 3 as well. Let's continue and work on a couple more examples and see how it works. Let's continue our examples by working on, for example, He2. He2 is made of 2 helium atoms, and He, it has 2 electrons. One is 2, and let me write another He, one is 2. To move faster, helium in the left, helium on the right, and I'm going to write 1s2 to remind you we have 2 electrons here. Then we are going to add our electrons to the atomic orbitals. 2 electrons here and 2 electrons over there. Next, we are going to say that we have totally 4 electrons, and we are going to add these 4 electrons to molecular orbitals. So this is the molecular orbital. So 4 electrons, 1, 2, 3, 4. Let's write molecular configuration for this one. Let me write this one is sigma 1s, sigma star 1s. So I'm going to say that sigma 1s, it has 2 electrons, and sigma star has 2 electrons as well. Bond order for He2 is going to be half of number of bonding electrons. It means 2 electrons here minus number of anti-bonding 2 electrons here. So it means 0. So whenever we have bond order 0, it means definitely it doesn't exist. And fortunately, we are going to have the same result with experimental fields. So this is something we may consider that. Right now, I'm going to talk about a short way method. If we are going to have He2 1 positive, He2 1 positive, so talking about the ion, I'm asking you, whenever you have the ions, if you want, if you practice enough, and this is something that you are really familiar with that, so always write He and He, and whenever you are going to remove 1 electron here, when we have the molecular orbital diagram for He2, you just need to remove 1 electron. You just need to remove 1 electron. And when it happens, you need to change that one like this. We are going to write this is He1 plus. It means we are going to have only 1 electron and remove one of these electrons here and have only 1 electron. So keep in mind, you can set up everything and then remove electrons over there. So right now, 1s1 for is going to be for He plus, and you are going to have 1 electron here. It means you are going to remove only 1 electron from the neutral molecule. So at this point, you are going to set it up by 1s, sigma 1s with 2 electron, and sigma star has 1 electron here. So this is something we may have, and bond order is already changed, and we are going to have 0.5. So definitely we do have He2 1 positive, it exists. Right now, I'm asking you to focus on this example, Li2. Let's see, do we have Li2? This is the one of the examples we may consider for s orbitals. Li is made of Li2 is made of 2 Li with atomic number 3. So let me write 1s2, 2s1, 1s2, 2s1. In some textbooks, they consider everything from the beginning, but it's not necessary because this theory is coming after Vesper and VB theories. Vesper is a stance on valence shell electron pair repulsion. VB stands on valence bond theory. It means we talk about the valence electrons only. So you easily can exclude, remove inner electrons. So I'm going to say that 2s1 for this lithium and 2s1 for other lithium. I'm going to add electrons here, and then we are going to combine, and we have like this one for molecular orbital. The main reason I wanted to share with you guys this example, when we are going to label for sigma and sigma star, because they are coming from 2s, I'm going to call that 2s. So sigma 2s and other one sigma star 2s. The number of electrons for each one, first one 2 and the second one there is 0. So you just need to cross that. Bond order is going to be half of 2 electrons. I'm sure you can easily look at the diagram and find what I'm talking about, minus the 0 electrons when there is nothing over there. The answer is making a magic number right now for lithium. Bond order 1. It means we may have Li like this one as well. So this is one of the benefits we may get from the molecular orbital theories. So I think that is enough, but if you want, you can practice some examples related to group number 1, 2, and working on the different periods, period 1, period 2, period 3. The last example for s orbitals, I'm going to talk about like beryllium 2 and see, do we have these diatomic molecules for beryllium? To do this, again, I may ask you to pause this video and work on your own example and double check with me after you have everything on the scratch papers. The main reason I ask you to write like me because you need to set up by yourself. Visually you may learn, but you need to do everything by yourself to master on this concept. Again, we are going to exclude the inner electrons. I'm going to say that Be on the left, Be on the right. So this is a 2s2 and that one is 2s2. We are going to have 2 electrons for first Be and another 2 electrons for other. We are going to add electrons and let's see what happens for molecular orbitals. So molecular orbitals in the middle, if you are going to have 2 electrons for this and 2 electrons for that. I'm going to label them sigma and sigma star because they are coming from 2s. I'm going to call them sigma 2s and sigma star 2s. 2 electrons for the first, 2 electrons for the second one. And as you see here, bond order is going to be half of 2 minus 2 means 0. So in other words, we don't have Be2 at all. Even in experiment, in the previous example, we had Li2, but we cannot predict Be2 exist. So like this one, let's start talking about the p orbitals. Again, I'm going to remind you, in my previous video, I said that for group number 3, 4, and 5, we are going to use this diagram that we do have pi molecular orbitals are in the lower level of energy. What does that mean, group 2, 3, 4? So one of the example I'm going to share, I'm going to talk about, for example, B2. Boron is group number 3, and I'm going to add 2 boron atoms to each other. So you may use nitrogen, 2 nitrogen atoms. Group number 4, carbon, 2 carbon atoms. And when you have them, you may have positive, negative ions, cation, anions as well. Because one of the most commonly used examples in the textbooks and most likely on the exams quizzes is nitrogen. Let me focus on the nitrogen in this short video. And I believe that after this example, you are able to set up for all other diatomic molecules as well. Nitrogen group number 2, 2 nitrogen atoms. So I'm going to write nitrogen group number 5, and we are going to have this molecular diagram. It's very important you know how to write how to set up the correct molecular diagram for each atom. So I'm going to add nitrogen with 7 valence electrons. So let me write like this: He, 2s2, 2p5, 2p3, or you may say 1s2, 2s2, 2p3. I want to say that you may write any way, any method for electron configuration, and we are going to focus on the last shells. Last shell, we call them valence shell and valence electrons, so we can easily remove the inner shells. So nitrogen, it has ended to 2s2, 2p3. So I'm going to write this nitrogen ended to 2s2, 2p3. Other nitrogen ended to same as well, 2s2, 2p3. Let's add electrons to each of them. 2, 2p3, we have 3 electrons here. And same like this. Before adding electrons to molecular orbitals, so let's call them by the correct labeling. Because it's coming based on the S, so we call that sigma, sigma star. They are made of 2s, so call them sigma 2s, sigma star 2s. Next one, they are made of p atomic orbitals. We have 2 in the same level, so it means they are pi and 1 is sigma. Again, we have pi because they are in anti-bonding, we call them pi star, and this one is sigma star. Right now, I'm gonna say that because they are made of 2p, we are going to add this subscript for 2p as well. So for all of them, they are going to be 2p. If you are going to have examples on the period number 3, it means 3p, 3s. So you are going to change the subscript. Right now, add electrons to each of them. Let's practice. So 2 electrons here, 2 electrons here. Totally, we have 4 electrons. I have to add 4 electrons here. We can easily do that one because we already practiced earlier. For S, 1, 2, 3, 4. Right now, I have 3 electrons on the left, 3 electrons on the right, 6 electrons. I have to add 6 electrons. I may ask you to please see that they are the same level of energy. I'm gonna add 1 electron to each one, then fill them out. 4 electrons, 5, and right now I have 6 electrons. I'm going to write what we have for nitrogen N2. Let's start from this. sigma 2s, then we have sigma star 2s, pi 2p, another pi 2p, and sigma 2p. Then if we had electrons over there, we can add them here. The number of electrons for each one: 2, 2, for the first one 2, for the second one 2, and for the third one is 2 as well. Some textbook call that one Py and Pz, and sigma always is Px. I already talked about this in the previous video. So you may call that sigma always Px and pi means Py Pz. Some videos or some resources, some textbook, they are going to combine pi and they are going to use only one pi in general, and they say you have 4. So they are going to say sigma 2s, sigma star 2s, pi 2p with 4 electrons, and sigma 2p as well. Which one is easier for you? You can consider that one. Both are correct. Excuse me. And last thing, talking about bond order, I'm going to calculate that half of number of bonding. Let's count bonding electrons here. 2 and 4, totally 6. So you may take a look at the diagram as well. 6 minus, sorry. So you may take a look at the diagram as well. So I'm going to call that 2, 4, and 2 totally. We are going to have 8 electrons. So I'm going to erase that one, and always you may double check everything by the diagram as well. So let's see, write that one like this. 8, look, 2, let me label that one by the pink color, 2, 4, 6, 8, and minus the anti-bonding. Anti-bonding here is the only anti-bonding we have is here means 2. 8 minus 2. So right now 8 minus 2 means 6 divided by 2, 3. So we are going to have the bond order for nitrogen 3, that it's going to be the correct answer based on the what we learned earlier and the experimental results. If we are going to add 1 electrons here, so for example, if I ask you to write N2 minus, so always I ask you, this is something in my in-person classes I teach. I ask my students to always draw and set up the molecular orbital diagram without having the ions, only like the nitrogen. And then when we have one negative, we are going to add manually 1 electron. So 1 electron should be added right now here. So at this point, we are going to calculate as well. If we have the N2 negative, we are going to do like this. If we have N2 1 positive, again, set up N2, and then you are going to remove 1 electron, the last electrons you already added, and remove that one. This is something we consider that one when we have for ions as well. I'm going to practice this one for the for the last example I have here for you guys. I already said that if we have if we have the molecules in group 3, 4, 5, we use that molecular diagram, and if we have group 6, 7, and 8, we are going to use this molecular diagram. And keep in mind, the only difference between this diagram and the previous one is this region, this part. I already talked about this in my previous video. Example, I'm going to talk about this. Let's talk about O2 1 positive. Let's talk about O2 1 positive. This is one of the most difficult examples if we want to share with you guys. When we have O2 1 positive, let me try to draw that one by this method. First, I'm going to draw O2, then I'm going to remove one electron from that. Why? Because here is one positive and I'm going to draw one electron from that one. So O2 means oxygen, oxygen, oxygen group number 6. So that is why I have to use this diagram. I'm going to say that 1s2, 2s2, 2p4. And let's quickly write the electron configuration for this one. Again, we cross the inner electrons, oxygen in the left, oxygen on the right, 1s2, 2s2, 2p4, 2s2, 2p4. Adding electrons, let's see how it works. 2, 2, 4, 1, 2, 3, 4, and for this one, 1, 2, 3, 4. Right now, before moving forward, let's label each molecular orbital we have. This one is sigma 2s, and this one is sigma star 2s. And when we are going to have one molecular orbital in the p level is going to be sigma and is coming from 2p, pi, 2p, pi, 2p, and if you are interested, you may say x, y, z, but it's not necessary at all. And the same thing happens on the top. Pi star, they are coming from 2p, and this one is sigma star 2p. And to make xyz, I'm gonna write like this one. Xyz, so y, and this one is z. Always 2px is making this. Right now, I'm going to add electrons to each of them. 4 electrons for S, so 1, 2, 3, 4. So at this point, 4 electrons on the left, 4 electrons on the right, 8 electrons. So I'm going to add 1, 2, 3, 4, 5, 6, 7, 8. So this is something we may consider for O2. If we look at the O2, we are going to have like this. But our question is O2 plus. Before I'm going to remove electron, I'm asking you, let's work on this example by yourself. Pause the video and calculate bond order for O2 and see what would be bond order for O2. I'm sure after calculations you are going to end to this one. You are going to say that 2, 4, 6, 8 minus 2, 4 and the 2 half of 4 means 2. It means oxygen looks like this one. So I wanted to say that you draw O2 correctly and bond order confirms that. But our question here is we are going to work on O2 1 positive. So this is a time to say that we need to remove one electron. So I'm going to cross that and I'm going to say it ends to 2p3 because we are going to have O positive, O1 positive. So I'm going to remove one electron here, and let me label that one by this blue color. I'm going to remove the last electrons I added, so I'm going to remove that one. If I remove it for O2 plus, we end to like this one, and let's calculate bond order for O2 plus. So everything is same minus the number of anti-bonding. Anti-bonding is 2 and 1, 3. So 2.5. It means O2 plus, O2 1 positive definitely exist. And whenever we are going to talk about stability, again, I'm going to remind you, when we talk about stability, it means we need to have more electrons in bonding and less electrons in anti-bonding. The only difference between O2 and O2 1 positive, it was the number of electrons in anti-bonding. In the previous one, we had 2 and here we have 1. So we can say O2 1 positive maybe is going to be more stable than O2 1 positive. They are something we can talk about this in the molecular orbital theory. I did review about 8-10 examples in this video and hope you learned how to set up and write the correct molecular diagram and calculate bond order by this method. Thank you for watching and hope you enjoyed that.